This is the last part of rotation we're going to see this week, and the last part of mechanics we're going to see for the 9 weeks, and that is rotational kinetic energy. So we're going to start with the kinetic energy formula from a couple weeks ago, 1/2 mv squared. We are going to turn these n's and v's into their rotational counterpoints. We talked about them this week. The first one is I. Then we also have what we did on Wednesday, the rotational velocity. And it's still got the 1/2 and the square in there, and that's going to give you the rotational kinetic energy. So anytime you have an object spinning, it has energy associated with it. Not only is it traveling in a straight line for kinetic energy, but if it is rotating, you're going to have some energy going to rotation as well. So I'm going to show you real quick what this I is about. We read about it on Wednesday. It was in your gallery walk. It was this document here, had all the weird formulas. But you'll note all of the formulas are some fraction of the mass radius squared. Now the moment of inertia is where the matter is located as it's spinning. So like the hoop, all the mass is around the outside, but for the cylinder, it's all concentrated evenly around. So they're all gonna roll a little bit different. That's what we've been exploring this week with rotation, and you saw a little bit with torque yesterday and how moving the mass affects how it creates that torque. So on your formula sheet, it looks like it says minus mr squared, but really it's just a fraction. So you're gonna fill in what fraction you're using based on what shape you are rolling. So it is important that we know the shape. Sometimes I'll write it with little boxes in there. It was originally had boxes, I'll get that fixed. But it does have some sort of fraction in front of the mass radius squared. So your first step to doing an RKE problem is to figure out what is this moment of inertia. Sometimes it'll be given to you as a number. Today we're gonna calculate it, you're gonna see it. There's a demo in the class with some meter sticks. Come ask me about it and I'll show you how it works, give you a real good intuition of what this actually is measuring. So for this last lab, it's on the back of the torque lab. It's ginormous looking, it's a lot of boxes. Essentially, we're gonna be rolling some shapes down a ramp, right? We've done that before, we've done it in a lot of different ways. We even did it this week on Wednesday with the moment, or the angular velocity. But this time, we are going to be tracking all the energy. So I got a little diagram here for us showing us all the energies. You're gonna have the ball at the top of the ramp, it's gonna roll down. But as it's rolling down, because it started at a height, it's gonna have potential energy. That's all the energy in the system. So we did this last Tuesday, concentration of energy with your Hot Wheels cars. It's going down the ramp, but now we know it's going straight down the ramp, so it has a kinetic energy, it has a velocity associated, but we also know it's spinning, right? You're gonna have these shapes that you've been messing with spinning down the ramp. And because it's spinning, it's gonna have this rotational kinetic energy. So ultimately what we're gonna find is we're gonna have a starting energy, the potential energy, and as it goes down the ramp, some energy is going into the orange bucket, some energy is going into the green bucket. But we also know, that was the question on the concentration of energy, you are destroying some energy. Where did it go? Some of it will be lost. We did work a couple weeks ago. This is also a lab about that. This is the work done by friction. We did the work done by gravity in that lab, but now we have friction. What you know of friction's a force, we've already done those forces. We're gonna be calculating how much energy are we losing to this friction. So as you're rolling it down, you're collecting a lot of data. You need the height, you need the time, you need the mass, you need the radius. Ultimately, that's gonna give you each section, each of these color forces has its own section of boxes. You'll see them labeled PE, KE, RKE. There's a pit stop to find the angular velocity from Wednesday, but it all comes together in the actual conservation of energy equation. Last week when we did it, it was just this half, but we know there's more going on now. We have a little bit more physics behind us. We've done work, but now we're introducing the idea that this object is spinning. So you're gonna be quantifying these three, measuring them directly in the lab, and coming up with how much work is done by friction. And we can go deeper in this equation. We do it in more college level physics where we go, well, the work is the force times the distance. If I know the distance, I can actually find the mu k and the coefficient of friction. We won't do that today. We're focusing on the orange equation and letting you guys manipulate the moments of inertia.